Delete recording. Whoa, thank you everybody. Thank you. Well, today I want to show you how to calculate the standardized precipitation and evaporation index for meteorological drought analysis. So in order to do that, just let's go directly to the work by itself. We need to prepare our data. Our data needs to have precipitation and monthly basis, mean monthly precipitation in millimeter. We need to have maximum temperature, which is basically in degrees Celsius, and also minimum temperature in degrees Celsius as well, in monthly basis. So while we have this three data, we will use this data in order to analyze the standardized precipitation and evaporation index by using RStudio. So our data has to be compiled, as you can see on the screen, in Excel file, and you have to save it in CSV. Like the first column has to be year. For example, for this station I may have more than 30 years from 1981 up to 2018, and the second column has to be months from 1 to 12, has to be arranged accordingly, and then the precipitation and the temperature. So first let me bring my precipitation and temperature data. If your data has a missing data, first you have to check all the necessary quality of the data analysis in order to have full-fledged information for the time span that you are going to do your work or your analysis. Therefore, here I may have the monthly basis data. For example, I want to analyze the data for the station called Dalifagi, which is found in Awash River Basin in Ethiopia. Let me bring my data one by one. This is not having any missing data, so that's why I'm trying. If you have a data having a missing information, first you have to investigate or fill your data, and your data has to be neat and clean according to all the necessary criteria. So let me bring also the maximum temperature of Dalifagi. Well, this is also pasted, and again let's bring the minimum temperature of this station. But well, copy and paste. So we have prepared data in one Excel file, as you can see. So let me save this data as CSV. From Model Limited. The station name is Dalifagi. Save it. Well, now let's go to RStudio. You have to open your RStudio, and this is a code that I have prepared in order to calculate the standardized precipitation index for a single station for one short time and long time span, that is for 1, 3, 6, 12, 24 and 48 minutes time scale. So the CSV file has to be prepared as I have showed you before, in column wise, as the year, month, precipitation, temperature, mean, and max in degrees Celsius. The first we need to install. Before that, what's SPEI? Here you can go to packages, then right here SPEI. You see it's the SPEI. So calculation of standardized precipitation evaporation index documentation is here, right? So you can read. It can be used for SPEI calculation and SPI, which is only using the precipitation data, standardized precipitation index, and it uses for fitting the function as the generalized logistic, which is logistic maximum likelihood function, and it can compute the potential and reference evapotranspiration using Hargrave's method and the like. So you can read everything was found here. So description of the file, so you can open it and you can see what the file looks like, about the package news, the balance, right, the data sets on the right. You can read how you can analyze your data, right? Here is the monthly precipitation data in millimeter, the months, the monthly an hour. All the description about the standardized precipitation and evaporation index can be found here as documentation, other documentation, so you can read everything as you want to know about how R and R stereo is basically calculating standardized precipitation and evaporation index and all the components that are basically related with it. So first we need to install the packages. So these are the packages. So you have to command install.package, SPEI, zoo, lubricate, and DP layer. Since I have installed it, I will not run this code. So you can run the code and you have to have the libraries. So after installing this, you have the library of SPEI, zoo, lubricate, and DP layer. So then you have to define the file paths, right? The input data, what I have prepared before, this CSV file is found in documents, meteorological drought analysis, and climate data variables. So you can see here the data station is found here. So if you can just copy these paths and paste it on the R package or the R studio on the input file. So I have already pasted it, and you can see this is the paths for the input file. So the output path is after the analysis where the result should be stored. According to your interest, you can choose the folder where you want to put or see or visualize your result. Then you have to read your monthly CSV file. So the CSV file has to be the function we need to read .csv, the input file. right? The input file is this one with strings as factors equals to false. So it has to be only the first column, which is strings. So it will arrange this in year and months as we have arranged first. Then what? Make a date column and compute mean temperature, right? So we have to call the date, right? df, which is found within the Excel or the CSV file at the date. So it has to be year and months, right? In year and months, and it will try to mutate or try to calculate the mean temperature, which is the maximum temperature plus the minimum temperature divided by 2. Then we need to compute the potential evapotranspiration using Hargreaves method. In order to do that, we need to have the information of the latitude, right? For example, here I want to calculate for Dalifagi. So in this folder, the station that I want to analyze is Dalifagi, and again the latitude, you have to bring the latitude for this station. The latitude in degree is 10.67. Let me copy this latitude and paste here. As per the location of your station, your latitude has to be bring here in decimal degree, right? Then the potential evapotranspiration will be calculated using Hargreaves method by using minimum and the maximum temperature as well as the latitude data, right? Then it will be having climatic water balance. So the climatic water balance is basically the difference between the precipitation and the potential evapotranspiration, right? So the climatic water balance has been designated here with BAL or balance equals to precipitation minus PET for each month scale. So we have to convert this climatic water balance into monthly time series, right? Which starts the climatic water balance, which starts as there is a year in one column, there is a month in one column. So the month has to be within the frequency of 12, since we have 12 months within a year. That's why the frequency has been given us 12. Then we need to compute the standardized precipitation index at multiple time scale. So the scale has to be 1, 3, 6, 12, 24, 48, whatever scale you want. 36, 9 has been missed here. If you want, you can add. Then this has to be in a scale. Then finally, then you have to extract the fitted SPEI. SPEI has to be fitted with the function having the output data given in date, year, month, precipitation, Tmax, Tmean, potential evapotranspiration, and water balance. This is one of the output that you have for SPEI analysis. Then with this you're gonna have also the SPEI. So the SPEI result will be saved in the output path as the name here. You can edit this name if you want, but for the time being I have given the name SPEI result for a single station plus CSV. So the row name has to be false. So in order to visualize, there is a quick plot for SPEI 12 months time scale. SPEI will be plotted in the y direction. There is SPEI. In the x direction, on the x-axis, you need to have the time or the date. So we will visualize. We will see for 12 months. You can visualize for each scale by changing this 12. If you want to see a 3 month scale, this 12 has to be changed into 3. If you want to see 24 months time scale, you have to change this 12 into 24. Then we need to classify. I want to visualize the drought condition. That means according to according to Thomas and Mackey in 1993, the value of drought indices, based on the value of the drought indices, the drought level has been classified. For example, if you have got the drought index, standard precipitation index, which is greater than or equals to 2, the drought level will be extremely wet. If it is within this range, 1.5 up to 1.9, very wet. If it is within this range, moderately wet. If it is from -1 to -1.4, moderate drought. If it is -1.5 to 1.9, severe drought. Or if it is less than -2, extremely drought. So this thing has shown the drought condition, or there is a drought level depending on the value of the drought indices that we have calculated. So we need to have the classification of a drought for each indices we have got from this analysis. That's why this is given for each boundaries or class of drought index. We have given the level of the drought, which is extreme, severe, moderate, and like this. Then apply this classification for all time scales, right? For 3 months, for 6 months scale or 12 months. Each calculations of every month's scale of drought has to be looped here to classify for each one. Then finally we have to save the result of drought classification for the station at the name SPEI results in the output path. You can change also this name as per your interest. So since I have the input file in CSV and the latitude 10.67, right here the latitude is the latitude for Dalifagi is 10.67, so that's why we provide the latitude for the analysis of Hargreaves for potential evapotranspiration analysis. So let's take this all and let me run it. With one click you can see in this console you can see it analyzes each step. So calculating the standardized precipitation evaporation days at time scale of 1 using kernel type rectangular, so you can read how it calculates for each month scale and using the log logistic distribution for fitting and analysis of potential evapotranspiration using Hargreaves method and the likes. The description will be here. So this one is also the plot. In this area there is a file bar, plot bar, packages and the like. So in the plot you can see how it plotted SPEI for 12 months time scale with the time and the SPEI data. So this range, which is less than -1.5, the drought will be very high, severe, and below this it's extreme, and above this 0, you can see there is no drought here. It's a wet condition. The drought is below this 0. So you can see the result. So let's see the result. The result is basically found in, well, the result is found in SPEI output. So yes, SPEI result in single station, you can see. We can say it's a Delphi station. So you can see here, right? There's a date, there's a year, month, precipitation, the input data, maximum potential evapotranspiration. Here you can see the climatic water balance is here, and SPEI1, 1 month time scale SPEI1, SPEI3, and 3 month scale SPEI6, 12 lag with the 12, and this 24 since, and SPEI48. So in order to analyze for SPEI for 24 and 48 months scale, you need to have a long term or a long time data, more than 30 years. That will be good. So this is the result for the SPEI value, so you can plot it if you want. And the SPEI result single station classification depicted here, and you can see here also the class, right? SPEI1 for 1981, month 1, near normal, the drought is near normal, right? And then month 2, in Ethiopian case, there has been a record in 1984. There is a drought, the whole over Ethiopia. So if you see the class, can you see the severe droughts, the moderate droughts? This one. Let me this one. So you see in each, and you can see right? So there's a drought here, right? Severe, moderate, at some months there is very wet, normal, moderate, extreme, normal. Here again there is severe drought, moderate drought, and here again you can see normal and moderate drought, and the likes. So this is a way that you're gonna have to calculate the drought using standardized precipitation and evaporation index. Thank you for your listening and attention.